One of the most important uses of mathematics is in what's called optimization. Optimization, to optimize something to make it as good as possible, make it its best. And there are actually a couple of types of that. One is maximizing something. The other one is minimizing something. For example, in economics, it's often the situation, you have a model and you're trying to maximize something. For example, revenue can be modeled mathematically. Yeah, and sometimes it's a fairly simple model and may not be very practical. Other circumstances might be more involved. Or if you're dealing with cost, you might want to minimize the cost of a particular thing, and there again, there might be a particular mathematical model for that. Now, I'm going to look at an example that's not necessarily all that practical, but it's at least fairly simple to set up. And if you've seen these videos and you've seen my writing on the whiteboard, you probably thought, boy, that guy really has horrible handwriting. I wonder what his drawing skills are. Well, here we can answer that question by looking at my little drawing of a pen that's it's actually kind of small here, but I won't bother with enlarging the picture. What we have is a pen for dogs and cats. We have sections of fencing that are separating the two groups of animals, and here we have a river on one side. They can get to the river, drink some water, watch the fish. We're assuming the dogs aren't going to swim away. Cats, so they don't like water. They're not likely to jump in there and create any trouble. We have a total of 100 feet of fence to use. The pens are open on the side that's facing the river, and so that side doesn't need any fencing. However, there is a section of the fence which separates the dogs from the cats. So there's no conflict there. Now, the drawing itself is, of course, totally unimportant. We can start by looking at a real simple representation of the same information here, where I've labeled W the length of 3 sections that are the 2 sides perpendicular to the river, and then the one part that's separating the 2 groups of animals. And then we have a longer side here. Well, not necessarily longer. We don't know what the dimensions of any of this stuff are at the moment. But the idea is, if you were given this fencing and you were asked to go and create an enclosure on the side of the river, how should you use the fence so that you maximize the area that you can have here and for the 100 feet of fence that you have available? Now, it turns out there is a maximum for this. There is no minimum necessarily. By taking the 2 sides and getting them closer and closer to each other, you can actually decrease the area as close to 0 as you want, or you could narrow these segments here so that the back side here, parallel to the river, is getting closer and closer to the river, and as that happens, the area is going to get smaller and smaller. It turns out there is actually a maximum. It can be mathematically proven. And not that complicated to set up. It's all we need for it is the algebra that you usually learn before you get to college algebra. So we'll start by, let me see here. Yeah, I think I have an issue with getting me out of my drawing here. I'll just open up another window, I think. Or another possibility is I can scroll down here and right here. Okay, so what we have here is, if we take the side that I labeled as L, and then to that we add the 3W, that has to be equal to a total of 100. So I'll lay my drawings down here now. W. This isn't the only way of setting this up. I just think it's the most logical, easiest way. And then just let L represent this whole length here. Now the area is going to, if we neglect the little bit of space taken up by this fence here, the total area of the enclosure here would simply be L times W. And we're trying to maximize that area. We start by this L plus 3W equals 100, which shows the relationship between the two variables. We don't have the area yet. The area could be written as area is equal to L times W. The problem with that is that that's a function of two variables, and we don't really have the techniques developed for dealing with that right now. So I want to get it to where we just have a single variable. So one way to do that is to solve this equation for L. We would have L is equal to 100 minus 3W. I'll go ahead and open up MathType and use that to do some of the work here. So that's going to be in a different window, so you won't actually see it while I'm typing, but it gives a nicer end result here. So okay, so I'm going to start with area is equal to length times width. Actually, I'll make that window a bit bigger here. Area is equal to length times width. As I mentioned, this has two variables, but we don't need both variables because we can replace L with this 100 minus 3W. So if we do that, again, I'm going to go in the window here and do some typing. So we have 100 minus 3W. Times W. So you just multiply this out using the distributive property, and we end up with a quadratic. So I'll do that. A is equal to 100W. You should either write this down or do it in your head as I'm working here, so that not difficult, just good practice. So our area function, we have now just two variables that we're interested in, area and width. In the end, we'll need to go back and figure out what L is, but that's no problem once we know what W is. And that will give us the answer of the enclosure, the dimensions of the enclosure that will maximize the area. Okay, so as you hopefully recognize, this is a quadratic function. If we graph it, it's going to be an upside down parabola, a concave down parabola, due to the fact that we have the minus 3 here. So hard to rewrite this in the more standard format. It makes absolutely no difference, but it's but if we write it in the more standard form for a quadratic, the quadratic term, the W squared term shows up first. And so we'd have area is equal to -3 times W squared plus 100W. And of course, this leading coefficient tells us that we have a concave down parabola like so. And we're trying to find the vertex right up here. Looks just like a parabola, right? Okay, so anyway. Leave that, try to get back to freaking MathType. Okay, so, well, it's really pretty straightforward from here. We need to find the vertex of a parabola. The vertex of a parabola is given by the relationship, usually written as x equals the opposite of b divided by 2a. Not to be confused with the a that we have here, and of course you don't see any x. So in this particular case, let me go back in here to math type and actually type that in. We will have this give me w is equal to the opposite of, well, b in this case is 100. And so we're going to have is the opposite of, fraction here, 100 divided by 2 times a. Well, a in this case is negative 3. And there it is, okay. If the area is negative 3w squared plus 100w, then this will be maximized, looking at the vertex, when w is equal to the opposite of 100 divided by 2 times negative 3. The negatives cancel out, and this becomes 100, well, actually, I guess 50 over 3, simplified form, equals 50 thirds. So the width is 50 thirds. The length has to satisfy the relationship that will, well, we have 3 sections that are w long, so all of those are going to be 3 times 50 over 3, which is just 50. And this is actually a very general thing. It turns out that in sort of rectangular enclosure like this, half of the fencing is going to be going one way and half of it's going to be going the other way. So if you take the 100, well, half of that is 50. That'll be the length. I'll go ahead and throw that in here. And should, of course, say these are feet. As a mathematician, I often don't worry too much about the units, but of course, units are important here. 50 by itself doesn't mean anything in this situation. So 50 feet, 50 thirds feet. So these 3 sections altogether make up half of the 100 feet that we have. Here's the other half. And so the answer to our question is the dimensions of the pins are, not sure if I have the right, this plural, the dimensions is definitely plural, are 50 feet by 50 thirds feet. And I'm not sure that the question I put out actually asked this, but, and the area is, but of course you can find the area just by multiplying this out. So we'd have 50 times 50 thirds. Well, 50 times 50 is what, 2,500? So the area is 2,500. 5 times 5 is 25. 10 times 10 is 100. 2,500 thirds square feet. And that's all there is to that. So again, very useful application of mathematics. Of course, you probably don't have too many circumstances where you have a certain amount of fence and you are trying to figure out how to keep your dogs and your cats separate from each other. I personally don't have a river flowing next to my property, but there are similar sorts of applications. Just in general, If you're trying to make a rectangle which has the largest area possible, it turns out that that's going to be a square. If you're trying to find a rectangle that has the largest area possible where we're not necessarily covering all the sides, or possibly we're covering all the sides, but we're also separating it out and partitioning it in some way, it turns out that in general, half of the available fencing will be used going one way, and the other half will be used going the other way, perpendicular to that. And you can actually go beyond this to show that the maximum of if you really wanted to maximize your enclosure, a circle turns out to be the maximum area that's enclosed by any one circumference. All possible shapes that could be designed. But that's a little bit beyond what we're ready to deal with right now. So that's our little video here on that, and see you next time.